Okay, so this is from chapter 3, section 10. We're solving quadratics or solving systems of equations and inequalities. Okay, Hannah, this is for you. This is Helen. And Abby. Hold on. Good. Anyway, we didn't get very far last time. We're going to be solving by different methods. The first method we did was down here with graphing, right? We graphed two solutions or two equations, and the solution was where on the graph. I don't know the answer, but we're really looking for on the graph. See? Where they intersect. Okay? That's when we saw graphically looking where they intersect. So now, example 2, we're going to do something differently. So you don't have to write down the whole story problem, just the important information. Okay? So example 2, we're going to recognize the association instruction. You can't see the problems, let's fix that. Since opening day, attendance at Pool A has increased steadily. Thanks, Devin. Is that important? Compared to graph Pool A's attendance, what graph would it be if it was increasing steadily? Linear. That's important to know. Pool A is linear. Now, attendance at Pool B rose first and then fell. What type of function is Pool B? A quadratic. A positive quadratic? Negative, because it rose and then fell. Concave down. So that's important, so write those two down. So A increased steadily, so B rose and fell. This is not good, doesn't have a doctor film. Okay, I'm going to do that. Maybe like 5 pieces of graphic for us, alright? So we have enough for 7? Yeah. Okay, the equation is modeling the daily attendance y. Do you again know what the variables represent? Is that important? So what's y? So right, daily attendance is y. What is x? What is x? Number of days opened, right? You can just say x is number of days opened. And the question, on what days was the attendance the same? So that's what we want to know when they're equal, right? If you're the graph this, we're looking for when they're equal. Okay, so we have here 2 different functions. We have a linear function for pool A, y equals 28x plus 4, and pool B is a quadratic function, and there is a negative, y equals negative x squared plus 39 plus 64. Oops, sorry. Okay, so we're not going to solve this by graphing this time. We're going to solve this by elimination. So this is a linear process. Solve by elimination. What we're doing when we're solving by elimination is trying to get one of the variables to be eliminated. Okay, we're going to zoom this up a bit. Let me start down by it down. So which variable is the easiest to be eliminated, the x or the y? There's lots of x's. There's different types of x's. There's x squared, there's x to the first powers. So I think that's more difficult. So I would say the y. is easier to eliminate. Right now, if we just add these up, we can all just have 2y. So what can I do to make one of those change so that when I add them up, I have 0 y's? So do make one of them negative, right? So that means I'm going to make the top ones less complicated. So I'm going to take the top one, and really whichever one in your choice, and times all of it by -1. And when I rewrite it, changing the signs of my pool A. It's now negative y equals, I'm going to make a space for the quadratic term, because the pool B is quadratic term, but pool A doesn't. So I make a space, and then 28x plus 4. So that when I line up pool B, I have all of my right terms lined up. My y's are lined up, my quadratics are lined up, because pool A doesn't have a quadratic, so there's a space there. My linear terms are lined up, and my constants are lined up. Did I not change the signs? I did not change the signs. There we go. And negative things. Those should all change to negatives. Okay, and then I just add them up. Negative y plus y is 0. And then nothing minus x squared is negative x squared. Okay, then we have x's. With y, how many x's we get when we add those up? Again, just think 39 minus 28. Reverse the order. 39 minus 28. 9 minus 8. So 11 x's. And -4 plus 64, Jenny? 60. Okay. How do we now solve? Daniel? We could, if it's a nice one, which is a different route, because completing the square is kind of, there's like lots of steps, right? Technically, yes, we could complete the square. But I would check first and see if this is a nice quadratic. Because generally, if it's a not nice quadratic, we complete the square only use the quadratic formula. But if it's a nice quadratic, what's the method that's real simple and not as many steps? Factoring, like on a quiz. However, with factoring, we want this to be generally positive, so can I divide every term by -1? Is that how? As long as I do to every term? So I get now 0 equals, now to make sure I change the signs this time. Positive x squared minus 11x minus 60. And then we can solve by factoring, like you'll see it on your test next week. As long as it's equal to 0, we can solve by factoring, or we can try to solve by factoring. If it's a nice one, meaning our x-intercepts are nice pretty integers. Okay? Then we'll find out right around the top row. So good, is that right? Up and then up, putting back one. Hunter. 1, and then we add to 100. Okay, so let's see. Two numbers that multiply to -60 and add to -11. Yeah. Very close, not 16 now. You're very close. 15 and 4, but which one has to be negative in order for them to add to -11? It has to be -15 to add. Because if 4 is negative, then it'll just be positive. Okay, so doing your answers. Okay, what's the next compact is? Add out between 1 and -15. 1 and 1 and 4. 1, give me what's the greatest compact of -60 and -15. Good. because they don't have negatives, so I would agree that I put a negative. Rachel, what about negative 60 and 4? So everybody's coming back to it. It is 4. And we can make sure it works. 1 times 4 is 4. 1 times negative 15 is negative 15. 1 times 1 is 1. 1 times negative 15 is negative 16. Then we get binomials. That would be equal divided by right to left side. Equal to 0. So you know what are the binomials that come out of our tic-tac-toe? Which is the and word. What's the operation? X. Subtract 15 and then x plus 1. Good. We just fill in these equations. How do we solve? Squiggly line. So equal, what's the minus? So equal to 0. So x is positive 15, and x is negative 4. Which one makes sense in our problem? Not the negative 4. Why does the negative 4 not make sense? Well, what does that represent? Does it represent people? It represents days open. So before they were open, both pool A and pool B had the same number of people attending, 0, right? So it doesn't make sense to talk about negative 4 days before they opened. X equals 15 would make sense. So our answer is, when are they the same? Pool A and B have the same attendance on day 15. That would be a great answer. A nice complete sentence. Yes? You try to calculate, if you can figure it out, then you do quadratic formula, or Rubik's square. Okay, we're going to solve the next one by a different method. So we did solving by graphing, which is just graph them and see where they cross, where they intersect. This one's solved by elimination. We eliminated the y here. The y is canceled out, so all we're left with is x's. Now, this one, we're going to, example 3, solve in a different method by substitution. So solve by substitution. I want to write these different rules down so that when the directions on your assignment ask you to solve by graphing, you know what that means. Solve by substitution, you know what that means. Solve by elimination, you know what that means. Okay, something for substitution you have to make sure to set up is at least one of the equations has to solve for the variable. So at least one equation needs an isolated variable. Otherwise, you're going to have to do some rearranging before you put it. So neither one of them are solved for y or solved for x. Then you have to solve one of them for y or for x in order to do this. Okay? Then what we're going to do is take, I would probably take this one, but it doesn't really matter. Take one of them and see, we're looking for where they're equal. So if they're equal, because they're intersected in this because of the graph, right? They would intersect. At the point where they intersect, the x and the y are exactly the same, correct? On the graph. Point here and a point here. Here, the x and y are exactly the same for the quadratic and the linear, right? And here, the x and y are exactly the same. And so they're equal. So when they're equal, this y equals 4 minus x. So what would this y equal? 4 minus x. So I'm going to take this y and I'm going to substitute it into that y. So instead of y equals, we write 4 minus x equals. And then stuff. X squared minus 6x plus 10. If they are both already solved for y, essentially we just drop the y's and write the x, both sides of x's, right? I ended up writing both these sides. I ended up writing this one and this one instead of equal to each other, because they both solve in the same variable. But sometimes they don't already solve for the same variable. So take the one that's already solved and plug it in to that variable in the other one. And then I just solve the equation. How do we solve quadratics? How do we solve quadratics? Alex? You can if you want. Yep. That's okay. That would be solving by completing the square. There's a lot of steps. How do we check and see if this one is an easy one or the next one? Factors, or how is it set up for factoring? Make sure it's equal to 0 to it's easy, right? So all of the setups for square roots, factoring, and quadratic formula are the same. Equal to 0. Completing the square is the only one that has a different setup, which is what Alex shared with us. The variable on one side, constants on the other. We can totally do it that way. It's just a little more painful, and there's like lots of steps, right? Completing the square. So I'm going to get all of my terms to the right-hand side, and I want to make sure, though, that this x squared is positive. It already is positive, so I'm going to keep it on the right. So then move my 4, then minus 4. And then move the x by adding x. And then put them right underneath their right terms. So the 4's cancel, the x's cancel. And I have 0 equals an x squared minus 5x plus 6. Is this a nice one? I don't know. Well, we always say equal to 0 as long as the y is gone. And we try factoring. Okay? Hannah, you tell me the top row here, the factor as you check out? Huh? Good, now 2 up. Good. Okay? Right then, give me the two numbers of multiplying 6, but add to negative 5. Yeah, is it that? I think that would work. Negative 3, negative 2. So that's an x. 1, 1, minus 2, minus 3. Let's put that in there, but he doesn't know how to do that. Okay, that's the answer. We haven't gone in reverse of how we normally read a book. Sorry. We need to take our tic-tac-toe and write it into factors. Okay. What's factors? Good. Something's wrong with the I can see your stuff. X minus 3 and something there. X minus 2. Yeah? You guys see the answers to this right now? Look at the nice ones. What are they? X equals positive 3, so it's just the other sign, right? And x equals positive 2. Which is by applying the 0 properties, setting this equal to 0, setting this equal to 0, and solving. As long as there is not a coefficient on the x, you should be able to see it. It's just the opposite sign. And because the coefficient on the x is going to be a fraction, so then you have to look at it a little bit. So there are 2 points where we have a solution. One is solving by substitution. I summarize down the steps. So essentially, one of them has to have an isolated variable. And you take that expression, y is equal to y, and whatever the variable is, and plug it in. And then you get everything on one side, if it's a nice one, and solve it. Okay? Any questions? Okay, the last way before we move to inequalities, example 4 is solved by graphing on a calculator. So we all have your calculators, we don't get one. And write down number 4. And I'm going to see the use a different calculator because the camera seems to be freezing my screen. I just don't know how to make this bigger. That's as large as it gets. Okay, solving with the graphing calculator. Okay, I'm going to put this over here and this right there. Okay, example 4. What we're going to do is put them in our calculator. So first we go to y equals on the calculator and type them in. So on your calculator, go to y equals and type in negative x plus 5, which shows negative buttons down here at the bottom. Negative x plus 5. We arrow down. And as a quadratic, negative x squared plus 4x plus 1. Before we graph, we have to make sure your window is okay. If you go to zoom, it's the middle button here up on the top. And number 6 is zoom standard. Zoom standard, that's what we want. Number 6. So everyone select number 6. That will put our window from negative 10 to positive 10 on the x and the y-axis. So there's our linear function. Here's our quadratic. So over that. Okay, now how many solutions are there? 2. Because they cross twice, right? They intersect twice. So I'm actually going to do it in a little bit so you guys can see it closer because I'm just going to go in there real quick. 2, 9, 2, 2, 5. See if that makes us any closer, we can still see all of it. Okay, great, perfect. That's what you guys see closer I'm doing. Above the trace line, it says in this order, the calculator you have is the same. We're going to calculate every intersection point. So go second trace. And we'll say intersect. And so we type them in. We hit graph. And now we're going to go second trace. And let's calculate. We're going to do these again. And then we're going to select number 5. You can go down to it. Or you can just push the number 5. Yeah, I'm just going to push the number 5. What does it say on the bottom of your screen? First curve. So it's asking to the line is on my little blinking above. When I move left and right and move up and down along the linear function. So if it's on the first one, type in, which is the linear function. I'm going to follow the linear function, pushing my arrows until my bug is on the intersection plane. We have just 2 different times, so I'm going to push the one on the left-hand side. And once I'm on the intersection point, I push enter. Now it says what? Second curve. And so you can go right and left, and you can see your bug is now on the quadratic. So again, you may not need to move your cursor, but you need to make sure you're on the quadratic and you're as close as possible to that intersection point. Let's enter again. And then it says yes. So if all of the bars are still the intersection point, we put enter for the third time. Essentially push enter 3 times. And what do we get? 1, 1, 4. 1 for our intersections. Then we have another intersection. So what's the process to get our calculator to do work? Second, trace. Which one do we select? Nothing. 5, intersection. Intersect. This time we need to go way over here. So we have 2 zeros. It's following the linear curve right now. Or the linear line, it's how it goes. All the way down. Almost there. Try to get as close as possible. The closer you are, the more accurate your calculator will be. Okay, press enter when you're on it. And the second curve, I look like I'm still there. Sometimes you have to move. Press enter again. Looks like it's still there, and so we press enter again. So it's our second solution. Third one. Another way you can write these, you can write them in both forms, x equals 1 and x equals 4, the x values. Okay, those are the 4 ways to solve quadratics, or to solve, systems. We can do it by graphing by hand. We can do it by graphing on the calculator. We can do it by elimination, limiting the y-uses when we eliminate. We can do it by substitution, taking one and plugging it into the other. Okay? We're going to have 12 problems like that on your homework. And we're going to move on to inequalities in a minute, but I was going to run a break, so stand up. If you are super quiet and not out in the hall, you can go to the drink and then come back. But please be quiet in the hall if you choose to rather. Okay. Okay, rules about the rollers. Please do not spin them on the tops of your pencils. I didn't have someone like their neighbor. Right in their eyes, dangerous, don't do it. Don't, do your stuff and hit your neighbors or do that. Watch it, watch it vibrate. It's really annoying really quick. Please don't do that, especially with spinning. Okay? We are going to take it to the different section, but since we're practically going to do it all together in the 2 days anyway, so it's kind of two lessons in 2 days, which makes sense. So, this is example 5, because we're still solving a system, but we change it up. So example 5, what's different this time? Inequalities. So, what does this symbol mean? Less than. The fact that ESS is actually going to look like the word less. So it looks like an L. It's less than. Does that one look like round? No. If you really want to get creative, you can go like this. It's gray, right? It's a G. It's greater. But really, it looks like now it's less than a good one, but now it's greater. Yeah, we write the G's like this. It's all the G's. Right? Oh, I'm going to go down here. Yeah, but you can put it more square. Okay, so we have two inequalities. Y is less or equal to this linear function, and y is greater than another linear function. The linear functions are nice because within y equals usually the inequality, and x plus b, what are these fractions representing? Rise over run on the slope. Which happens with that. Rise over run. That's the second thing we use to graph them. The first thing we use to graph them is the constant. What does the constant represent? It's an intercept, it's not the x. The y-intercept. So first you can plot the y-intercept, and then from there we can use the x-intercept, the slope. So you get more points. Okay, there's a difference though between normally when you did inequalities in junior high, when you did one dimensional on the number line, you had open when you had these types of points, and closed circles when you had these types of points. Right? The same applies here to we're two-dimensional. So it's not just a point, it's an open line, so dashed, are similar to this, and solid are similar to this. Dashed, solid, dashed, solid. So ask me which one is it, dashed or solid, okay? So, let's first take a colored pencil. You already have grid paper, so let's have you set up your graph first. You can look at the colored pencil actually. And set up the x and y axis. I think -5 and +5 is fine. Hopefully they intersect there. That's how I do my graph. But, you know. Yeah, that'll be fine. Okay. Label it X and Y. Make sure you show what you're counting by. We don't always count by ones. We need to label the counting by. So, someone who reads your graph knows how to read it because you have set up your intervals that you're counting by. Then choose color pencil, and I'm going to color from mine. I'm going to box that one with color. You can shade it lightly. The blue one is going to be this one. Where's my first point? If I was to graph y is plus 3 equals 1/2 x plus 3. Positive j on the y-axis, right? That's our y-intercept. And then from this point we use the slope. What is the slope? So up 1, right 2. Up 1, right 2. Up 1, right 2. Now we reverse it and go down 1, left 2, down 1, left 2. Right, and it should look like a line, down 1, left 2, down 1, left 2. Okay, now look at this line. Should we connect these dots with a solid line or a dotted line? Solid or dotted? Please show me. The top line, is it going to be solid or is it going to be dotted? What is it? That's equal to solid or dotted? Solid, right? So take your ruler and connect them with a knife. Oops. Okay. Yeah, this is like me. Okay, I will not use the line tool. I will use the marker and try to draw the straight line I can. It's not too bad. Okay, now we're not done. We need to shade the graph. So before you add open circles and shaded circles, now I have to figure out where to shade. We do that by doing a test point. The easiest test point is 0, 0. So over here, I'm going to do a test point. I'm going to plug in 0, 0 and determine if this point is true or false. So y is 0, plug it in, less than or equal to 1/2 times 0 plus 3. As long as 0, 0 is not on your line, or close to the line, I would use it. If it's on the line or too close to the line, then my next choice would be something on the y-axis, so that would be axis for 0. So here I get 0 and less than or equal to 3. Is that a true or false statement? So this is true, true. And then this is false. True or false? Is that true or false? 0 is less than or equal to 3. True or false? Should be true, right? So you shade where it's true. Do it lightly with that same color. You shade where it's true. So I'm going to use my highlighter. I have a crayon, I guess. Okay. Under here is our point, which we said was true. It's on the bottom side. No, it's too dark. Do it really lightly. You're going to try to highlight it. I guess it'll be lighter. So everything on the same side the line as that point you found to be true is also true. Inequality doesn't just have one solution, it has infinite number of solutions. So everything in the area you're shading would also, if you plug it in, make the equation true, including points on the line, because it's a solid line. If it was a dotted line, it would not include points on the dotted line. Now we're going to pick a different color and do the same on the same graph. I'm going to pick something that doesn't quite off to the blue. And we're going to graph this guy and determine solid line or dotted line and shade it. Okay? So what's the first point I should plot? History where? The y-axis, or y-intercept. So right here, -3. Okay? Now this was my slope that I'm going to use. Good, so what does that mean? How does -5 work with rise and run? The negative head? Down 5 and then 1, 2. So we always go right for the run. So put the negative sign to the numerator. So we'll go down 5 and then run to the right 2. Well, we can't do that on our graph. So how about we go up 5 and then which direction do we go? Left 2. Oh, look, intersection point. And then up 5, also off the graph. Okay, we're going to connect these with the line. Really, we only need 2 points for a line, so it's okay. Is this going to be a solid line or a double line? Dotted. Is that sign language? Is that in sign language? Code? Is this code? Okay. Okay, so make sure you check the sign always. If there isn't dotted, it's because there's no equal to. So we're going to connect these with a dashed line. I kind of feel like I don't leave enough space here. There we go. There, so I want to have to do a test point. Can I use 0, 0 again? 0, 0 is not on my dash line. Can I use 0, 0? Yes. If it's available, it's not on your line, let's use it. We're going to do at this point, true or false to the red dash line. So I plug in wherever y is, if it's 0. It's greater than -5/2 times 0 minus 3. The reason that 0, 0 is nice is because that always goes away. 0 is, you have to know what that sign is. So less than or greater than. Does it look like no? No. So it's greater than. True or false? Show me. T or F. Is 0 greater than -3? True or false? Okay, well, 0 greater than -3. True or false? 0 is greater than -3. Good. True. So this point is again true. Where should I shade? Just ignore the blue. We're just looking at red. Where should I shade? To the right side of the red line. Do it lightly. This pink. Now it is, oops, let's get that a little bigger actually. The whole right side, so even the section where we didn't shade before. So, you know, that's what you're doing lightly because we're going to take a dark color. If you need to trace the neighbors, take a dark color. The solution is where both of them have the same common shaded area. So because we have 2 lines that are intersecting, we actually have like 4 sections. Which section has both highlights in it? That's right side, right? It's almost like a triangle. So take a darker color and shade all the way up to, we have a dotted line going down there, we have a solid line right up there. The dark color should be your solution. So you want to do the first 2 lightly, and then the dark one is your solution. But make sure we can still tell where your intersection points are and where that's solid or dotted. Is that making sense? If it's true, you shade where the point was. If you get false, you shade the other side where the point wasn't. So we got true right here. So because this point was on the right-hand side, that's why we shade on the right. If this point was false, then shade the left side. So you shade where the true section is. Okay? Good question. We're going to do one more. Hopefully we're going to call some here so we can practice. So one more. So this is example 6 of these of the last one. Oops, what way was that? Let's get a roll right there. You also have some on your homework that just have one inequality. I figured we just jump to the hard ones. So it's the same way, right? You just graph it, dotted or solid, and shade it. And it could even be a quadratic. You need to do a dotted parabola. Yeah, the graph is exactly the same. You need to know the vertex and your x-intercepts, but if it's less than or greater than, with no equal to, it should be a dotted parabola. If it's equal to, you do a solid parabola. Okay, so pick a color, highlight it. After you write it down, I'll write it down in this color. So the later ones are nice because we can see, we don't have to do a table, we can see a y-intercept and then just use the slope. Okay, equation. Where should I put my first point on my graph? Okay. Good. On the x or the y-axis? Good. So on the y. So you guys probably don't have your graph set up yet, so I'll pause for just a minute. So a good graph. Now, if you do graphs on your homework, and well, I guess it's a worksheet. The graph is already set up for you, so that's nice. The other thing is by hand. Sometimes you want your window not negative positive 5, but you want your window negative 10, positive 10 to actually see where they intersect. The worksheet already has the window set up for you, so that should be okay. Alright, so you should have a point in -2 with the first color comes from. And then we want to use the slope. What is the slope that we should do? From that point, how do we move? Up 5, right 2, good. And I like that you start at -2. You don't start back at the origin. That's why we put the y-intercept first, so we have a starting point. We go up 5, right 2. And then we continue until we're off the graph, and we're already off the graph. So, if you tell me things, should this be a solid line or a dotted line? Solid or dotted? Good. Should be solid. Move it equal to. So take your ruler and just solid. With arrows, because those along the right hand the line. Now, is the test point, is 0, 0 not on this graph? On the line of the strip? Yes. So 0, 0 is one to use. Again, if 0, 0 is not available for you because it's like on the line or it's too close, you can't really tell if it's on the line, then pick another point on the y-axis. Like you can pick 0, 4. Because I'll put the 0 for the x to make sure that's a lot easier. So let's do a test point, 0, 0. 0 is the chain what that symbol means. Cancels out. Okay. What does this symbol mean? Greater than or equal to. So true or false. -2 or 0 is greater than or equal to -2. True or false? True or false? 0 is greater than or equal to -2. 0 is greater than negative? True. Yeah, true. Okay, so this point is true. We shade the true side if we had gotten a false. Where would we shade? The other side. But since this point is true, we shade the point. We want to shade whatever's true. So take that going very lightly. Very lightly all the way up to the line. Shade it. Graphs look so nice. And when you're ready, pick your second color pencil. Make sure you write it in that color or highlight it in the color so it's color coded. Put your y-intercept on, that means your slope. Okay, so then where's our y-intercept this time? Positive 2 is what their slope. Up 1 over 2. Up 1. Intersection, right? Up 1 over 2. Let's go down 1, left 2. Down 1, left 2. Down 1, left 2. Should I do a solid line or a dotted line? Dotted. It's not always one of each. Sometimes they can both be solid or they can both be dotted. So dotted. Which means on that line there are no solutions. If it's on a solid line, any point on the solid blue line are also solutions. But on this line that's dotted, there are no solutions on that line. It's all the way up to the line, but not including the line. So in the test point, can we use 0, 0? Yes, for then 0 is greater than 1/2 times 0, that cancels, plus 2. True or false? 0 is greater than 2. True or false? 0 is greater than 2. False. We want to know false entirely. So this point here is now false for the red line. The false point is below the red line. Where is the true area that we should shade? Above. So always shade the true area. So above, shade it lightly all the way through. The 2 lines intersecting is we have 4 sections. Which one have both shadings in it? The top left. So take the darker color, maybe train with the native with the darker color. And then the top left, now it's not perfectly straight because we start here on the dotted line and then we abruptly go up along the solid line. So I will be expecting to see the darkest color as your solution. But I should still be able to tell the difference between a dotted line, a solid line, which you will see your intercepts. So make sure your graphs are nice and neat and important, just like you're doing right now. You're absolutely nice. Okay, does that make sense? Okay, so we have a few problems in the book on the first ones that are not the shading inequalities, on the equations, specifically equations. And this worksheet already has the graphs prepared for you. You just have to graph them and do the shading. So I'll be looking for the darkest color is where your solution is. So if you have your homework calendars, you saw those, or your own personal planner. Page 211, you have 12 problems on equations. And then this worksheet on inequalities. Page 211, 1 through 12, and this worksheet on inequalities. So in total, the worksheet has 17, I think. 17. The front side of the worksheet has 2 of them graphing because it's a system. Once you get to the back side, it's only 1. But if you use number 10, you're only graphing 1 on each graph, but you still have to shade. Do you have a question? That's volume 1. Yeah. That's the question. So we're back to volume 1. So technically random, I'll always do volume 2. Once it comes second semester, mid-January, we'll always be using volume 2. But right now it's just hit and miss. Okay, so while you have your colored pencils, maybe start on the first one on this worksheet. You'll get time to do one before you leave. Yeah. I want the shaded part, the solution to be done. If this is like yellow and green for like that real first, that's fine, as long as you can see that you do the initial shading. And then the dark section needs to be. Well, I can see there's horizontal and vertical stripes, but I can't tell which is the darkest. So then I need you to take a colored pencil and shade through the darkest one so it's easier for us to see. Yeah, I'd rather do pencil or crayon because it's still kind of hard for me to see. Yeah. Yeah, I can see that. So that's okay. Darkest. And you can make a key on the top. You are always using the same 3 colors. You can put a key on the top that says like this color is blue is the solution. You want to make sure that it doesn't have any questions. Yes, Daniel?